Japan, China, and Singapore. Currently, he is working with Toshwin Analytical Private Limited, Mumbai, as a product consultant. So we welcome you, sir. And this was a brief introduction of our guest speaker. I request, sir, to please share your valuable knowledge and experience with our participants. Over to you, sir.
Thank you, sir. Thank you for the wonderful introduction. Thank you very much. First of all, let me keep on record my sincere thanks to the principal of Government College of Pharmacy, Karat, and Professor Manoj Charde for giving me an opportunity to be a part of this FDA from a faculty FDP Faculty Development Program, which is being organized from 28th of February to 4th of March. You already had one day of session yesterday, and today morning also you had some wonderful lectures. And what I see from the schedule is just before lunch, you also had a very good lecture on basics and applications of HPLC by Dr. Ganesh. So chromatography is all about separations. I hope all the participants have got a very good understanding of what is chromatography, where the chromatography can be applied, what are the basic applications. All these are, I hope all of you know very well. And chromatography is a very, very old technique. The birth of chromatography was in the year 1905. And now we are in 2022. So already 117 years have already passed. So during this long period, lots of developments have taken place in the field of chromatography. Developments have taken place in column technology, sample introduction technology, detection technology, development of very, very powerful software systems. All these have taken place over a period of long time. And today we have a very, very powerful chromatography system, which is capable enough to separate, analyze, identify even the most complex naturally occurring compounds. And specifically telling naturally occurring products are very, very complex multi-component samples. And they are very, very complex samples, but our systems are so powerful that we can easily analyze even all those very complex natural products also. So when we talk about chromatography, any form of chromatography, whether we talk about gas chromatography, whether we talk about liquid chromatography or any other form of chromatography, all of us know we have two different phases that are the basic requirements for conducting a chromatographic analysis. So I'll start sharing my screen now. All of you can see this. My screen is visible to all of you?
Yes, sir, visible.
Okay. So today I'm going to talk about a very, very interesting topic, a gas chromatography connected to a mass spectrum. It's a hyphenated system. We know, all of us know there are so many different hyphenated systems available today. We talk about GCMS, we talk about LCMS, we talk about ICP-MS, we talk about TGMS. There are so many different hyphenated systems are available, which are very, very powerful separation coupled with identification techniques. So specifically when you talk about GCMS or LCMS, the chromatography part, the GC part or the LC part is responsible for the required separation of the compounds present in the sample. And what is the mass spectrometer doing? It is only doing the identification of the separated compounds. So when we talk about a hyphenated system like GCMS, we are coupling two different techniques together. One is an identification technique and one is a separation technique. GC is responsible for separation and MS is responsible for identification. Now, so any chromatographic technique is a physical separation method. Why we specifically say physical separation method? Because in chromatography, there are no chemical reactions. Only physical interactions are there. Absolutely no chemical reactions. That's the reason why I specifically say it is a physical separation method. And that involves the distribution of components. Now you have a sample and the sample contains more than one component. It can be 2 compounds, it can be 10 compounds, or it can be 100 compounds. So when you have a sample which contains different compounds, and when you do a chromatographic analysis of the sample, the compounds get distributed between 2 different phases. That's a very basic requirement for conducting a chromatographic analysis. You require a stationary phase, you require a mobile phase. When you talk about HPLC, your mobile phase is going to be a liquid. It is a combination of liquids. But when you talk about GC, it is only a single gas that we are going to use. And it's inert gas we are going to use. But in the case stationary phase, either it can be a solid material or it can be a liquid material in the case of GC. And if you will see in the bracket, I've put 2 different figures, 10%, approximately 10% against solid and 90% against liquid. It's an approximate weightage I am giving. 10% weightage is given to a solid stationary phase and then 90% weightage is given to liquid stationary phase. It simply means a solid stationary phase can be used for about total 10% of the applications, whereas remaining 90% of the total applications can be carried out with the help of a liquid stationary phase. So that means a liquid stationary phase is more versatile, more widely. For example, you talk about pharmaceutical analysis, you talk about food chemistry analysis, you talk about perfumery analysis, or environmental analysis. Normally, we try to use a liquid stationary phase. So it has got wide applications, very widely used by different customers, different segments. That's the reason why I'm approximately giving a 90% weightage to liquid stationary phase. Whereas a solid stationary phase has got a very limited segment for application, especially gas analysis. When it comes to very complex gas analysis, it can be refinery gas separation, it can be hydrocarbon separation, it can be noble gas separation. Any type of gas analysis, we prefer to use a solid stationary phase. So there is a very specific segment. So that is the reason why I am giving a very small percentage of weightage, 10% to the solid stationary phase, whereas liquid is given 90%. Now, depending upon the mobile phase and the type of stationary phase that we are going to use, chromatography can be classified into various forms. Some of the important forms I have mentioned here. When you are using a gas as the mobile phase, and when you have a solid material as the stationary phase, the principle of separation is based on adsorption technology. And the technique is known as gas-solid chromatography, GSC. And this is the technique we normally use for gas analysis. Again, we have got a gas as the mobile phase, and now we are going to use a liquid as the stationary phase. Then the principle of separation is going to be partition. And then the technique is known as gas-liquid chromatography. So gas liquid and gas solid, the difference is only in the type of stationary phase. Either it is a solid or it is a liquid. When it comes to LC also, liquid chromatography also, you are going to use a liquid as the mobile phase. You can use a solid as a stationary phase. Again, the principle is going to be adsorption, and the technique is going to be LSC, liquid solid chromatography. A silica column is a fine example. You must have listened to that in the morning session, pre-lunch session. Liquid solid chromatography. Again, we are going to use a liquid as the mobile phase and liquid as the stationary phase. Then the separation, the principle is partition, and it is liquid chromatography, LLC. We use liquid as the mobile phase. We are going to use a porous polymer having well-defined pore sizes as the stationary phase. And the principle of separation is based on exclusion, size exclusion. That is separation based on the molecular size. And the technique is known as size exclusion chromatography or gel permeation chromatography. It's a very important technique, especially in polymer characterization, GPC or SCC. Again, we are going to use a liquid as the mobile phase, and we are going to use an ion exchange resin as the stationary phase. Then the principle is based on ion exchange. Either it can be cation exchange or it can be anion exchange. And the technique is known as IEC, ion exchange chromatography, but nowadays we only call it as IC, ion chromatography. Okay, ion exchange chromatography and ion chromatography. I mean, there is a small difference also. I'm not getting into that, going into that. Then we have a liquid mobile phase. We are going to use a thin plate, maybe an aluminum plate or a glass plate, coated with a uniform thin layer of silica. Principle is based on adsorption. It is TLC, and I think you had a wonderful lecture on HPTLC yesterday from Dr. Saikat. HPTLC, thin layer chromatography. Now it has become high performance thin layer chromatography. So there are different classifications of chromatography based on what type of a mobile phase we are going to use and what type of a stationary phase we are going to use. Now coming back to gas chromatography, that is gas phase chromatography, what are the goals of carrying out this? To separate mixtures of organic compounds. But sometimes when I tell this, it can be slightly misleading for the customers. Then they say whether inorganic compounds cannot be separated by GC. But so to answer that question, first of all, we need to understand GC is gas chromatography is a technique for volatile compounds. Non-volatile compounds cannot be directly analyzed by GC. It is not possible. Number one. Second, gas chromatography can be applied only to samples which are thermally stable. That is the second requirement. One is the volatility, second one is the thermal stability. Unless these two conditions are fulfilled by the compound, it cannot be analyzed by GC. It can be analyzed, it has to be analyzed by HPLC. So that is from that perspective, most of the inorganic compounds are totally non-volatile. You talk about, for example, you talk about potassium dichromate, you talk about sodium chloride, magnesium sulfate. These are all salts. It can be an oxide, it can be a salt, it can be a chelate, it can be anything. It's an inorganic complex out of purview of GC because they're all totally non-volatile materials. They just cannot be analyzed by GC. But GC can be analyzed for very, very few inorganic compounds which are already in the gaseous form. For example, air analysis. We all know air, the composition is about 79% nitrogen and 21% oxygen. And these two can be separated by GC at room temperature using a 1 meter molecular C5A column and a thermal conductivity detector. Without heating, I can separate these two compounds and you will get two beautiful peaks. And it is an inorganic substance, but the compound is already air, it is already in the gaseous form. I can separate carbon monoxide and carbon. It's a very, very important application in petrochemical industry and fertilizer industry. I mean, it's a very, very critical application. Carbon monoxide and carbon dioxide detection at very, very low concentrations. And we can do it by people do it by GC, and it is an inorganic substance, but they are already in the gaseous form. So those compounds which are already in the gaseous form, inorganic gases, can be separated by GC. Otherwise, most of the other inorganic compounds cannot be separated. So, but most of the organic compounds are basically volatile, but they are also what we need to understand. There is a cap on the molecular weight. Any compound has got a maximum molecular weight up to around 600 only can be analyzed by GC. If I get a organic compound, for example, if I take a protein or a material, protein or peptides, they are all organic in nature, but the molecular weight is so high that they naturally automatically become non-volatile, and GC is not the technique. You have to go for LC or LCMS for that. So it is basically for small molecules having maximum approximately molecular weight up to around 600. Otherwise, it becomes non-volatile. We can detect individual analytes and identify and quantify using reference standards. And this statement is equally applicable to LC also, because we can get a wonderful separation by selecting the right type of column. But how are you going to identify the separated compounds? For that, you require reference standards. Okay, that is the case in the case of GC. That's the case in the case of LC also. Now, just a brief this thing about this slide shows what is the layout of a normal gas chromatography system. So you have a carrier gas, that is a mobile phase, is called the carrier gas. It is an inert gas, and we do not have much choices like in the case of HPLC. HPLC, you have plenty of choices, but in the case of GC, you have got a maximum 3: nitrogen, hydrogen, helium. That's all. You have to select one among them, and that is present as a pressurized cylinder. The cylinder is connected to the GC, and the gas from the cylinder is coming to the GC, entering the system to the injector port. And injector port, you are going to introduce your sample, you are going to inject the sample, a very, very small quantity of sample you are going to introduce either manually or automatically. And that injector is heated, and you have to optimize the temperature. And at that temperature, whatever sample you are going to introduce, it will immediately vaporize. And the sample vapor and the gas, suppose you are using nitrogen as the carrier gas. Nitrogen is coming from the cylinder. That is also coming to the injection port. So the nitrogen and the sample vapor will mix together. It will go to the column. And the column is always inside an oven, because column is to be separately heated. Your injection port is to be separately heated, and your detector is also to be separately heated. So in a GC, we have got 3 different heating mechanisms. And the actual separation will take place inside the column, depending upon what type of stationary phase you have chosen. And different compounds will move at different speed, and it will come out of the column at different times. We all know retention time. That is the time at which the compound is eluting out of the column and entering the detector. And depending upon the detector is also heated. And there is a thumb rule, your detector temperature should be more than the final column temperature, at least by 15 to 20 degrees centigrade. This is required only to prevent condensation of your sample vapor. It's very, very critical. Otherwise, your detector cell will get contaminated, and lot of noise reproduction will be there. Sensitivity will go down, and you will have to call the service person to clean it. So to avoid that, we need to keep your detector temperature at least 15 to 20 degrees more than the final column temperature. And depending upon the compound concentration, the detector is going to give an electrical signal, which will be processed by your software and PC. And on the right-hand side, in this slide, you can see some more cylinders connected to the detector. Like hydrogen is required, air is required. These are all called detector gases, or sometimes people call it as auxiliary gases. So we have a carrier gas which is connected to the injection port, and few other gases, auxiliary gases, connected to the detector port. That is basically for the detection mechanism. Okay. Now, most critical part in a chromatography, whether it is you are talking about HPLC system, you are talking about GC system, I normally consider the column is the most important part of this equipment, because the column is ultimately giving you the separation. The desired separation is given by the column, not by the injection mechanism, not by the detection mechanism, not by the software, nothing. Column is responsible for giving the desired separation. So column selection is extremely critical in chromatography. Unless you select the right type of column, you will not get the right type of separation. So column chemistry is very important. You need to understand what is the column chemistry, what is the sample chemistry. There has to be a match between these two. Then only we can get a meaningful separation of all the compounds present in the sample. And when you are selecting a column, we have different considerations in our mind, whether we should go for a packed column or we should go for a capillary column. In the case of GC, we have 2 types. One is capillary and one is packed. Capillary is more popular today, because many other complex samples can be separated only by a capillary column. And what is the stationary phase? In GC, we have got hundreds of stationary phases. So what is the stationary phase you have to use? You have to decide that. And what is the stationary phase film thickness? When you consider a capillary column, the stationary phase is present inside the tubing as a very, very fine film, very thin film on the inside wall of the tubing. And it has got a very definite thickness. It is in terms of microns. Today, we have columns from 0.1 micron film thickness up to 5 micron film thickness. Different film thickness columns are available. You have to decide what is the film thickness required for your separation. And what is the column inner diameter? The capillary column is a very, very fine thin tubing made of silica. And there are 4 different inner diameters available. 0.1 mm internal diameter, 0.25 mm inner diameter, 0.32 mm and 0.53 mm. So you need to decide what is the inner diameter of the column tubing you require. And the last one is the column length. Today, capillary columns are available from 10 meter up to more than 100 meter. And you decide what is the length, 10 meter, whether you have to use a 10-meter column, 25 meter, 30 meter, 50 meter, 60 meter, like that. You have to have all these considerations in your mind while selecting a column. Okay, now this is just a slide showing what is the type of capillary column. I mean, it's made of fused silica, and you can see inside there is a coating, and that coating is the coating because of the stationary phase. And this coating thickness is in terms of micrometer. As I told you, 0.1 micrometer up to 5 micrometer thickness columns are available today. And it has got very, very high efficiency. You can get wonderful separation even for a very complex sample. You get a very thin, very, very narrow and sharp peaks you can get. And these are some of the important features of a capillary column. See, I'm not getting into too much of discussion on the column. Column itself is a very, very vast topic. And injection mode, sample introduction systems, there are different ways by which you can introduce the sample into the GC. Split injection mechanism, splitless injection mechanism, PTV injection mechanism. PTV stands for Programmable Temperature Vaporizer Injection System. Direct injection mechanism, cool on-column injection mechanism. So there are different types of injection mechanisms, that is sample introduction mechanisms available depending upon the application. But when it comes to most of the time pharmaceutical analysis or perfumery analysis, we normally go for a split injection mechanism. Okay, so that is the most widely used injection mechanism, the split injection. Splitless injection mechanism, when we talk about food safety analysis, food products, when we analyze food products for residual pesticides, because these pesticides are already present in extremely low concentration like ppb level or even less than ppb level. In those type of analysis, we go for either a splitless injection mechanism or a PTV mechanism. So there are different types of simple sample introduction systems, sample introduction mechanism. It all depends upon what is your application. Okay. Now, what type of detectors? We have got different detectors for GC also. Flame ionization detector is the most commonly used detector. It's quite a sensitive detector for most of the organic compounds. Then we have thermal conductivity detector, TCD. Once upon a time, it was considered as a universal detector, but today, no. But the only problem with TCD, it can detect anything except carrier gas. The problem is sensitivity is very less. Then we have flame thermionic detector, FTD, which is selective and which will only respond to samples containing nitrogen and phosphorus. So it is also called nitrogen phosphorus detector, NPD. Then the next one is flame photometry detector, flame FPD, which will respond only to sulfur and phosphorus containing compounds. These are all selective detectors. Then we have got electron capture detector, the most powerful detector in the case of GC. Electron capture detector is very, very selective for electrophilic compounds. Any compound which has got affinity for electrons, which can attract electrons. For example, say for example, chlorine containing compounds, any halogenated compounds are electrophilic in nature. And if these compounds are present in extremely trace level, ECD can be used. ECD, but we have to be extremely careful because ECD contains a radioactive isotope, nickel-63. So to import and install an ECD on your EGC, first of all, you have to get a clearance from BRC because of the presence of a radioactive material. Otherwise, a wonderful detector can go to femtogram levels of detection. Then comes our the detector, mass spectrometer detector, which is a true universal detector today. And that is what we are going to discuss now. Advantage of mass detector. All other detectors are called conventional detectors. And now when we talk about a mass detector, what is the advantage of a mass detector over all the other conventional detectors? All the conventional detectors are very, very sensitive. I told you ECD is extremely sensitive. All other detectors are very sensitive. So they can give a very wonderful analysis. You can give wonderful sensitivity for even very low level concentrations of your targets. But the problem is the detector cannot tell you what is the compound. It becomes your responsibility to identify the compound using a reference standard. But getting a reference standard all the time is a Herculean task. I'll give an example because once we separated a perfumery compound which contained about 180 compounds. We got 180 peaks at the baseline when we injected a very small quantity of a perfume in a high resolution capillary column. So that means that perfume is a combination of 180 different chemicals. Where are you going to get the standards from all this? For all this, is extremely difficult. So a normal conventional detector can only give a very good separation, but identification becomes a major problem. And that is the place where a mass detector is going to have an upper hand. It is going to score over all the conventional detectors. It can also give you very, very sensitive analysis. It is not going to compromise the same level of sensitivity it can attain in a mass detector. At the same time, it can also identify the separated compounds without the requirement for a reference standard. I'm just underlining the sentence. The mass detector can identify the separated compounds without the requirement for a reference standard. That means qualitative analysis can be carried out and the separated compounds can be identified by the mass spectrometer. For that, you don't require a standard. But just keep in mind, if you want to do a quantitative analysis, then reference standards are required. The moment you say quantitative analysis in analytical chemistry, whether it is chromatography or spectroscopy, for example, UV spectroscopy, IR spectroscopy, atomic absorption, or ICP, or LCMS, or GCMS, whatever it is, the moment you say quantification, you need to prepare a calibration curve. And for preparing a calibration curve, you require standards. So in the case of GCMS also, or MSMS also, if you are going to do a quantitative analysis, you require standards because we have to construct a calibration curve. But our aim is only to a qualitative identification, then you don't require standards. So it's a very, very important point to keep in mind. What is the simple definition of mass spectrometry? I know all of you must be knowing. Yes, we are trying to refresh it. The basis of MS, that is mass spectrometry, is the production of ions that are subsequently separated or filtered according to their M/Z ratio, that is mass to charge ratio, and then detected. The resulting mass spectrum is a plot of the relative abundance of the produced ion as a function of the M/Z ratio. I'll just make it very simple. The basis of mass spectrometry is the production of ions. That means the basic requirement for a sample to be analyzed by using a MS system, the sample has to undergo ionization. Whether it is GCMS or LCMS, it has to undergo ionization. And when the sample undergoes ionization, or we call it as even fragmentation, when the sample undergoes ionization, different ions are going to be produced. Depending upon the structure of the molecule, the different ions are going to be produced. And all these ions will be having different mass numbers. They are not same, they are all different. So when the molecule undergoes ionization, you are going to get a mixture of ions having various mass numbers. And we are going to separate, we mean the mass spectrometer is going to separate all these ions on the basis of their M/Z ratio or mass number. And they are all sent to the detector. And the detector that what we are using in GCMS, the mass spectrometer, it is called an EMT, electron multiplier tube. An electron multiplier tube is the detector that is used in a mass spectrometer. So all these ions are separated on the basis of mass number, and they are all taken to the EMT, electron multiplier tube. And this EMT is going to give a output, and that output is nothing but the mass spectrum. And the mass spectrum is a fingerprint. It's a fingerprint of the compound. When we go for Aadhaar card, we give our fingerprint, and that fingerprint is our identity. Because my fingerprint can be only reproduced by only me. In a second, another person cannot reproduce my fingerprint. So it's an identity for me. Similarly, the mass spectrum that is produced from a compound is going to be its fingerprint. And that is going to be the basis for identification. We are going to identify the compound based on the mass spectrum that is produced. And what is the mass spectrum? It is nothing but a two-dimensional graph, like an XY graph. So on the x-axis, we are going to plot your mass number, And the y-axis, we are going to plot the relative intensity of ions produced. Relative intensity or abundance. The intensity of ions produced will be plotted on the y-axis, and the mass number will be plotted on the x-axis. That forms the mass spectrum of the compound, and it becomes its identity. Okay. So basic requirement, I've already told you, the compound has to undergo ionization, and there are different ways of ionizing the compound. So before we go to the ionization techniques, what is the objective of a GCMS analysis? There are three different objectives. Number one, separation and identification of compounds in the given sample. It's a qualitative analysis. So tomorrow, if you get a pharmaceutical compound, pharmaceutical sample, suppose it contains 5 different compounds, compound A, 1, 2, 3, 4, 5. So what is your aim number one? Your objective number one is to separate all these 5 different compounds very, very satisfactorily. And then having got the separation, you also have to identify those compounds. What is compound number 1 up to compound number 5? That means separation and identification of the compounds present in your sample. That is a qualitative analysis. That is objective number 1. What is objective number 2? Quantification. Now you have already separated the compounds, you have already identified the compounds, and now you are going to quantify how much of each compound is present. So that becomes a quantitative analysis. This is objective number 2. And what is the third objective? Higher sensitive residue analysis. Today we are talking about different residue analysis. Residue analysis means where your target compounds are present in extremely trace level. It can be, for example, if you take a food product, it can be a vegetable, it can be a fruit, it can be meat, or it can be marine products. They all contain pesticide residues today. And all these pesticide residues are present in extremely trace concentrations. They are at residue levels. And our instrument should be capable enough to identify, separate, and identify and quantify these compounds, targets, which are present in very, very trace concentrations. That is called a residue analysis. Forensic applications. It is a very, very sensitive residue analysis, forensic applications. Some of the clinical applications. I mean, they are all the compounds, the targets are present in extremely low level concentration, and your system should be capable enough to separate, identify, and quantify them. So that is a sensitive residue. That is objective number 3. Now, what are 4 S values when we talk about mass spectrometry, GCMS? So 4 S values. Number 1 is sensitivity. What is sensitivity? Changes. Very simple definition of sensitivity is change in the detector response whenever there is a change in the concentration of your target. Otherwise, people may say my detector is very sensitive, and what is meant by sensitivity? This is the simple definition. Change in the detector response whenever there is a change in the concentration of your target. Second one is selectivity. Relative freedom from interference. May not be very applicable to pharmaceutical sector, but when you consider a compound like a food sample or an environmental sample, and you are trying to quantify a certain target in that, there are plenty of other unwanted chemicals present in the sample which can cause interference, and these are called matrices. So matrix interference, they can interfere in the determination of your target. If that actually happens, your determination will not be correct. Whatever quantitative result you are going to get will be totally wrong. So what is required is these type of matrix interference should be avoided. That is what is known as matrix elimination. We can do it. There are ways and means by which we can get rid of the matrix interference. So when you are doing an analysis, you have to ensure that there is absolutely no interference from any unwanted chemical. Then you can say your method is very selective. You are confident whatever value you are going to get is absolutely right. That means your method is very selective. Third one is speed of analysis. That's the order of today. In corporate world, the most important factor is time. How much output you can increase per person output. We measure it by PPO, per person output. How much output you can increase by end of the day. So for example, if your one sample is taking 1 hour to complete, That means if you are working from say 9 o'clock in the morning to maybe 5 o'clock or 6 o'clock in the evening, how many samples you can complete? Because each sample is going to take exactly 1 hour. So maximum maybe 5 or 6 samples we can complete, because there's a heating process, heating, cooling, all those times you have to take into consideration. So maybe around 6 samples or at the most 7 samples you'll be able to complete by end of the day. But if we can somehow reduce the analysis time from 60 minutes to say 10 minutes, that means my sample, instead of taking 1 hour to complete, it is getting completed, analysis is getting completed in 10 minutes time. That means in 1 hour time, I can analyze at least 5 samples minimum. That means end of the day, instead of analyzing 6 samples or 7 samples, I may be able to analyze 25 samples or 30 samples. My output is going to increase 5 times. And that is what is today's corporate requirement. Increase the output. So we have some provision for that also. There is something called in the software, there is something called fast mode of analysis, where we can reduce the analysis time without compromising the resolution. You are going to see one slide going forward. And the last S value stands for solution, not just instrumentation. See, you are going to buy an equipment like, say, for example, if you buy an LC-MS-MS or GC-MS-MS or ICP-MS, all these equipments are going to cost a lot of money. Lot of investment is required. They are all high quality, the price wise, they're all very, very expensive equipments. And when you spend so much of money and buy an equipment, and when that equipment comes into your lab, it should not remain on the table like a white elephant. It should be utilized properly, and it has to give you a total solution for your analytical requirement. Then only you will get the return of investment. You will get the whatever money you have spent. You have to benefit from that. So it has to give a total solution for your problem analytical requirement. That means proper utilization, total solution. So these are the 4 S values: sensitivity, selectivity, speed, and solution. So when we normally talk about a GC, we get 2 important information about the sample. And all of us know that. All of us. We get retention time of the compound. We also get signal intensity, a detector response. So these are the 2 things we get normally from a normal chromatogram. When we analyze the compound by GC, analyze the compound by normal HPLC, you get these 2 informations. You get the detector response and the retention. So you get a 2-dimensional information. But when you consider a GCMS, you will be getting one more information of the compound, that is the mass spectrum. So in addition to retention time and the signal intensity, we are also going to get the mass spectrum of the compound. And using this mass spectrum, you can easily go for identification of the compound. So it has always got an upper hand. The GC-MS combination has always got an upper hand on the conventional GC. I am not underestimating the power of conventional GC. It is a very, very powerful technique. But the only drawback is it cannot give you an automatic identification. Where you require standards, that's only the limitation. But when it comes to GC-MS, that is also overcome. You can identify the compound without the reference standard. Let us consider the flow chart of a SQ. SQ means single quadruple. When you talk about GC-MS, LC-MS, there can be single quadruple systems or triple quadruple systems. So what I am discussing today is only a single quadruple system, GC-MS. Otherwise, triple quadruple means GC-MS-MS, like LC-MS-MS. Again, now flow chart of a GC-MS system, single quadruple. Now consider you can, and the diagram you can see, you have got a sample. And that sample contains many different compounds, more than 2. It can be 2, 10, 15, 20, whatever it is. Many compounds are present in the sample. So what is required? What is the first important requirement? Objective number 1, you remember, separation. And that's for getting the separation, you have to inject the sample into the GC. Because separation is the responsibility of the column, not the mass spectrometer. So initially you have to inject the sample into GC. You can also see one more arrow there, direct inlet. And that arrow is going to ion source. I will talk about it a little later. So right now you see the sample is going into the GC. GC contains a suitable column. You have already selected the right type of column. And the column has separated these compounds. And one by one, the compounds will come out. When it comes out of the column, it will go to the mass spectrometer. And the mass spectrometer contains three important parts. Number one, ion source. Second one, mass filter or mass analyzer. And the third one is your detector. Okay. So when the compound and all these three, you can see ion source, mass filter, and the detector, they're all connected to a very, very powerful vacuum system. And why this vacuum is required, that also I will show you one slide. Vacuum is also a very, very important feature. So when the compound comes to ion source, it will undergo ionization in the ion source. So ion source is the place where your sample is going to be ionized or where your sample is going to be fragmented. There are different types of ionization techniques. Ionization techniques used in GCMS and ionization techniques used in LCMS are different. LCMS has got different ionization techniques, GCMS has got different ionization techniques. They're different. So your sample will undergo ionization in the ion source, and depending upon the sample type, depending upon the structure of the compound molecule, different ions will be formed, and all these ions will be having various mass numbers. And now these ions are going to be separated on their mass number by the mass filter, or sometimes it is also referred to as mass analyzer. And all these ions from the ion source will be ultimately taken to the detector, which is an EMT, I told you, is an electron multiplier tube. And this detector is going to give a signal, and that will be processed by your PC, and you get an output. That output is your mass spectrum. That output is the mass spectrum. So that mass spectrum becomes the basis for the identification of the compound. So this is a normal flow chart of a single quadrupole GCMS system. Okay. Now I am coming to ionization mode. The most important ionization mode in GCMS is called an electron impact ionization mode, EI mode. By default, it will come. Whichever company, whichever model you are purchasing, whether you are purchasing a GCMS from A, B, C, or D, different companies, they all will give you electron impact ionization as the default mode, because it is the most widely used ionization technique. Very hard ionization technique, very high energy involvement is there. At the same time, you'll also get structural information or qualitative identification from electron impact ionization. And many of the people are doing qualitative identification. That is why electron impact ionization is used as the most widely used ionization technique. And that's the reason why it is given as default. So it will come along with the equipment. Now there is a different ionization technique which is optional. This will not come by default. You have to separately purchase. You have to buy for that. You have to pay for that. And that's called chemical ionization. And that chemical ionization is a very soft ionization technology. Very low energy involvement is there. And this chemical ionization, there are two types. One is positive and one is negative. Positive chemical ionization, it is called PCI, and negative chemical ionization is called NCI. Now, positive chemical ionization will give you information about the molecular weight of the compound. That's all the utility of PCI. PCI is used to find out what is the molecular weight of the compound. It is not used for qualitative identification. It's only used to understand what is the molecular weight of the compound. Very, very widely used in pharmaceutical industry. They use both EI and CI. They do the normal EI analysis, go for a library search to understand to identify what is it qualitatively. Then the same sample can be analyzed under CI mode, PCI mode, and then you get the complete information about the molecular weight. Then you get a 100% foolproof identity of the compound. So they can be, EI and CI are used as complementary to each other in pharmaceutical industry. Now NCI, negative chemical ionization, is only for the trace analysis of electrophilic compounds. When I talked about GC, I mentioned one detector, electron capture detector, which contains a radioactive isotope. Extremely powerful for the trace analysis of electrophilic compounds. any compound which has got the affinity to attract electron, affinity for electrons, which can attract electron. The same type of analysis, same type of compounds can be analyzed in GCMS with the help of a NCI mode, negative chemical ionization mode. So that's it is quite a useful technique, especially in food analysis, in food chemistry, food analysis. There are so many different halogen containing pesticides present in our food products, and they are all present in extremely trace level. And then we employ a negative chemical ionization to identify and quantify those type of compounds, but may not be very widely used in pharmaceutical. But in food industry or food analysis, food chemistry applications, NCA is very, very widely used. So electron impact ionization, the compound is coming from the column. You can see the compound is represented as a red color sphere. That's a compound, that's a molecule that is coming from the column. And when it is entering the ion source, the ion source contains two filaments. There is a filament at the top, there's a filament at the bottom. The filament at the top is electrically heated, and at a high temperature, it starts emitting electrons. And these are called thermal electrons. And they have got a very, very huge quantum of energy, 70 electron volt energy. They are very, very high energy electrons, thermal electrons, and these electrons will be emitted by the filament at the top. And what is the filament at the bottom doing? The filament at the bottom is actually collecting it or actually pulling it down. So all the electrons that are emitted by the filament at the top will be collected by the filament at the bottom. So the filament at the top is called the emitter filament, and the filament at the bottom is called the collector filament. So there is always a flow of electrons, and when the molecule is passing through, these electrons will go and bombard the molecule. And normally we know for most of the organic compounds, the ionization potential is somewhere around 15 to 20 electron volts. And these electrons are having 70 electron volts, so almost 3 to 4 times more energy. And because of the impact, the molecule will be broken down. And these molecules will be broken down into different pieces. And we are calling them as ions or fragments. And all these ions or fragments are having different mass numbers. So ultimately, you will be getting a mixture of ions in the ion source, which are produced from your original molecule. Now, the next task is to separate these ions on the basis of their mass number, and that will be done by your mass analyzer or mass filter. And all these ions will be sent to the detector, which is an EMT, and the detector is going to give an output, which is a mass spectrum. What you see at the bottom of this slide is the mass spectrum of methyl stearate, methyl ester of stearic acid. So you can see that electron impact ionization is a hard energy technique, because 70 electron volt energy electrons are bombarding the sample molecule directly. The sample molecule will undergo near total fragmentation, what we normally call it as near total fragmentation. Nothing will be left in most of the cases. It undergoes almost 100% fragmentation. And you get so many different fragments of the molecule, depending upon the type of molecule, and you get a very, very complex mass spectrum. So what you see here, you can see so many different, each line represents one ion. Say, for example, there is a line at 74, that is a fragment which is having a mass number 74. And then there is another on 87, 143. So the different ions you can see. Out of all these ions, the ion with mass number 74 is having the maximum concentration. And that is theoretically given 100% as the intensity. We are theoretically assigning a value of 100% to the ion which is having a mass number 74. Now, considering mass number 74 as 100%, the software will calculate what is the intensity of 87 mass number, what is the intensity of 69 mass number, what is the intensity of 143 mass number. This is what is known as relative intensity. And that is what is plotted on the y-axis. And on the x-axis, we are going to plot the mass number. So you get a mass spectrum, and it becomes a fingerprint of the compound. Okay. When it comes to, so normally if you want to qualitatively identify We have a facility for library search. Mass spectral libraries are provided in the equipment. NIST libraries are there, Wiley libraries are there, and you get more if you even for the latest NIST version of the library, there will be more than 3.5 lakhs of mass spectra are already stored in the library. So once you get a mass spectrum of your compound, when you go for a library search, within few seconds, it will tell you these are the possible compounds. So you can, that means you are able to identify the compound for which you have not used the reference standard. Okay. So, but electron impact ionization is you have to analyze the sample only by electron impact ionization if you want to go for a library search and qualitative identification. You cannot do that with a PCI mode. Okay, so that's what I'm coming. PCI mode can be used only to understand what is the molecular weight of the compound. So when it comes to PCI mode, and normally when we talk about the GCMS analysis, GCMS operation, our carrier gas is only, that is our mobile phase, only high purity helium. We require only one gas. Like in JC, we require multiple gases, nitrogen, hydrogen. I mean, those type of gases are not required in the case of GCMS. We require only high purity helium. So only one gas is required, and it has to be high purity. Okay, quite expensive also. Now, when you go for a positive chemical ionization operation, you require a separate reagent gas. But that's a very small cylinder. The consumption will be extremely small, extremely small, and the cylinder will remain for a very, very long time. And why the reagent gas is required, I am going to tell you. And what are the reagent gases that are commonly used in PCA? There are three. Number one, and most popular one, most widely used one is high purity methane, CH4. Second one is isobutane. Isobutane compared to methane is little more costly. And third one is high purity ammonia, NH3. Ammonia is very, very rarely used for some selected type of compounds. Otherwise, not very commonly used. The selection will be between isobutane and methane, but isobutane is costly. So people normally prefer to go for high purity methane. Methane is not that costly also. So why this reagent gas is required is what we do before injecting the sample. If I want to do a positive chemical ionization analysis of a certain compound, before we introduce the sample, we introduce a extremely small quantity of the reagent gas into the ion source. That means methane. If I am going to use methane as the reagent gas, a small quantity of methane is introduced in the ion source. This will be done automatically. You don't have to do it yourself. All this will be done automatically. And when methane goes inside the ion source, and now you know 70 electron volt energy electrons are available there, and these electrons will bombard the methane molecule. And in turn, the methane gas will undergo ionization. There will be different ion molecular reactions taking place, and this methane will produce different reactive ions which are unstable in nature. Different reactive ions are going to be produced, out of which two different reactive ions are produced in maximum population, CH5 plus and C2H5 plus. Okay, and these two reactive ions are produced from methane in maximum population. More than 85 to 90% population of CH5 plus and C2H5 plus will be produced. And then we introduce our sample, and when the sample goes inside the ion source, there is a large population of these reactive ions, CH5 plus and C2H5 plus, which are by and large unstable. They want to go back to a more stable form. These ions will collide with our sample molecule, but that is called a secondary stage of collision. Energy of collision comes down to around approximately 15 to 20 electron volt. So that is why it is called a soft ionization technique. So when these ions are colliding with the sample molecule, normally what happens, the extra proton in the reactive ion, CH5 plus, if you take out one proton from CH5 plus, it will become CH4. It goes to a stable form. Similarly, if you take out one hydrogen, one proton from C2H5 plus, it will go back to C2H4. It's a very, very stable form. So when these ions are colliding with the sample, these extra protons will be given to the sample and they will go to the stable form. CH5 plus will become CH4 and C2H5 plus will become C2H4. And in this process, our molecule will get an additional proton. Addition of one proton, we all know the molecular weight will increase by 1 unit. One proton addition means increase by 1 unit. And that is why we normally get a M plus 1P. Okay, M plus 1P. So this is what actually happens. CH4 is introduced, it undergoes ionization, and it produces reactive ions. They will collide with the sample molecule, and the extra proton is given to the sample. So something like you can consider it as a protonation reaction. And these reactive ions will go back to a stable form, and then your sample molecule will attain 1 unit more. That becomes M plus 1. Now, what you see at the bottom is the same methyl stearate spectrum. We have seen methyl stearate spectrum under EA mode. You have seen so many different fragments are produced there. But if you look at the positive chemical ionized PCA spectrum of methyl stearate, you can see there are very, very few fragments are coming. And the most prominent fragment you can observe at the extreme right-hand side of the spectrum, 299. You can see a very prominent fragment at 299. And if you take out, that is an M plus 1P. So if you take out M1 minus 1, M plus 1 minus 1 is equal to M. So 299 minus 1 is equal to 298. 298 is the actual molecular weight of methyl stearate. So without any problem, you are getting the actual molecular weight of the compound. Okay. So that is why positive chemical ionization is used only to determine, to understand what is the molecular weight of the compound. It is not used for qualitative analysis or qualitative identification or library search. That is not. So it's only to understand the molecular weight of the compound. So this is, this is how these reactive ions are formed. First, methane will be bombarded by electrons. CH4 will undergo ionization. Then there will be subsequent ion molecular reactions. And then there will be formation of CH5 plus and C2H5 plus. These are the two dominant ions which are produced in very, very high concentration, more than 85 to 90%. So there is a large population of these reactive ions in the system. Now, this is a comparison of a certain compound analyzed by EA mode and PCA mode. You can see that upper one is EA mode spectrum. The lower one is a PCA mode spectrum. The sample is compound is same. So you can see whether you get a very complex spectrum using EA mode, whereas using a PCA mode, you get a very, very simple spectrum. Okay, and one more thing, what for your understanding, PCA mode, positive chemical ionization mode, the most prominent fragment can be an M plus 1P. Whereas in the EA mode, the most prominent fragment is called a base peak. So please understand. So most prominent fragment in the EA spectrum is called a base peak, and the most prominent fragment in the PCA spectrum is called a M plus 1P. So normally when you go for a library search, the software has got a certain algorithm. So it will try to identify what is the base peak, the most intense band, most intense peak, the most intense ion is considered as the base peak. And based on that, your subsequent, what you call the filtrations will take place, and finally the compound will be identified. But when you take, suppose if you take a PCA mode, PCA spectrum, and then you go for a library search, what will happen? Library doesn't know whether it is a PCA spectrum or an EA spectrum. It doesn't understand that. So it will only look at the most prominent fragment now, and this prominent, or based on that prominent fragment, you will go for a library search. But what you need to understand, in the PCA spectrum, the most intense peak is not the base peak, it is only an M plus 1 peak. Whereas in the EA spectrum, the most intense peak is the base peak. So in this case, for this particular sample, I think a lot of background noise is coming. So if you look at this particular compound, if you look at the EA spectrum, 125 is the most intense peak in the EA spectrum, and that is the base peak. Whereas you look at the PCA spectrum, 331 is the most intense peak, that is the M plus 1 peak. So 331 is not the base peak. Base peak is only 125. And identification of the base peak is critical for library search. So if you take this PCI mode, software will consider 331 as the base peak. And in reality, it is not. So you will get a wrong identity. That is why we say PCI spectrum, please do not go for library search. So only understand what is the molecular weight. And if you want to really identify the compound, then go for a library search, do the analysis only by electron impact ionization. Coming to negative ion, NCI, negative chemical ionization, is basically for electrophilic compounds which have got affinity for electrons, can attract electrons and form a negative ion. So when you select the NCI mode to the software, the lens polarities will be automatically adjusted and it will collect only the negative ions and the positive ions will be discarded. So even if there is a electrophilic compound present in extremely trace level, that also will form a negative ion by capturing some electrons, and these negative ions will be collected by the system. So you can have a very, very sensitive analysis for electrophilic compounds, even though they are present in extremely low concentration. So after the ion source, now these are the three major ionization techniques in GCMS: electron impact ionization, which is the most widely used one; positive chemical ionization to understand what is the molecular weight; and negative chemical ionization for the analysis of electrophilic compounds at trace level. And the next part of the system is your mass analyzer or mass filter. So it is a very, very integral part of your mass spectrometer, which is responsible for the separation of the ions produced in the ion source on the basis of mass number. So that means, your sample has undergone ionization in the ion source. Ion source now contains many different ions. They're all having different mass numbers. They will be separated by this mass analyzer. There are different types of mass analyzers. Magnetic sector is the double focusing magnetic sector, which is extremely costly. Normally, people don't use it in industry. Is not normally used in research institutions and basic research, and the price also will be very, very prohibitive. Okay, so it is basically for academic interest and basic research. But in industry, the most important and most prominent mass analyzer is quadruple QP. That's why we call it as QP, quadruple system. It's a benchtop model. Then we have time of flight. Time of flight is basically high mass range, like biopolymers, biological samples like protein analysis, peptides, high molecular weight compounds. We can use a time of flight mass analyzer. But time of flight mass analyzer, the ionization technique is normally different. It is a MALDI system. Matrix assisted laser ionization, desorption ionization. Matrix assisted laser desorption ionization technique. And that's why normally called as MALDI-TOF. MALDI is the ionization technique and TOF is the mass filter, time of flight. Normally for very high molecular weight compounds and biological samples. Then ion trap system is also a benchtop model. But ion trap is also a good instrument, but only thing it has got some inherent problems when it comes to qualitative identification. And that's a very reason, quadrupole has become a very, very preferred system today. So a single quadrupole MS, that is what we are discussing now, a single quadrupole MS. On the extreme left-hand side, what you see is the ion source. Your sample has undergone ionization. It has produced a different number of ions. They're all having various mass numbers. It's a mixture. And then you are separating all these ions are separated on the base of their mass number by the quadrupole. You see that quadrupole in between. And on the extreme right side, what you see like a triangle, that is your detector system. That's your EMT, electron multiplier tube. And ultimately, what is required is all the ions in the ion source should be taken to the detector, and the detector should give a response, which is the mass spectrum. So for you to understand a little more, this is a quadruple. This is how a quadruple system is. It's basically 4 rods. That's why we call it as quadruple, 4 rods. And they are all at equal distance from each other. One is at the top, one is at the bottom, and one rod is on the left-hand side, one rod is on the right-hand side. That's the arrangement. And they're all equal distance from each other. And that alignment is very, very critical. That alignment is extremely critical. We should not, normally we don't touch your quadruple system and the user has no access to that. Even the service person also normally doesn't go to the quadruple system. Even if there is a very minute disturbance in the alignment, it can cause a lot of problems. So because it's very, very critical. Okay. Now, what we are trying to do, how this quadrupole is separating these ions or taking out the ions and the ion source. For that, what we do, see, now I said one rod is at the top and one is at the bottom. That forms one pair. And one is on the left-hand side, one is on the right-hand. That forms the second pair. So on one pair, we are going to apply direct current, DC voltage. And on the second pair, we are going to apply radio frequency, DC and RF. So on one pair, we are applying DC, another pair, we are applying RF. So at any point of time, there is a certain ratio of DC to RF. So for a certain ratio of DC to RF, only one particular ion will come out. It will have a very, very stable trajectory. It will be moving through the space between these four rods without touching them. And finally, it will go to the detector. You can see on the right-hand side, you can see something like a cup. That is a detector. And you can see the green line. The green line is the trajectory of a stable ion. So it is passing through the space between the four rods without touching that, and it is going to the detector. So we have successfully taken out one ion from the ion source. What about the remaining ion? There are plenty of ions still remaining in the ion source, and we have to take out all those within a very, very short period of time. Otherwise, another compound will come out of the column. So before the second compound comes out of the column and it enters the ion source, all the ions from the previous compound should be removed and the ion source should be kept empty. Otherwise, there will be mismatch. So what we do, to take out all the ions from the ion source, we continuously change this ratio of DC to RF. So, and this we are going to do at a very fast rate. And when you are changing this at a fast rate for 1:1 ratio, 1:1 ion will come out having a stable trajectory, will go to the detector. And the whole process will be completed in maybe a microsecond or a millisecond. It's a very, very short period of time. That means we have successfully taken out all the ions from the ion source and they are all given to sent to the detector. Ion source is empty. Now next compound will come from the column. That will also undergo ionization. The process gets repeated. So this is how we take out. So this is the responsibility of the quadruple system. So their responsibility is only to separate all these ions on their mass number and send it to the detector. And what are the capabilities of a quadruple system? It can carry out excellent qualitative analysis for a multi-component sample. If your sample contains different compounds, that is what they are, multi-component samples, and they can carry out an excellent qualitative analysis. And they can provide a quadruple system can provide a very, very reliable library search system. I will consider it as the most important feature of a quadruple system. That is how sometimes your ion trap can have a problem. But your quadruple system can always offer you a very reliable library. That is why it has become very famous for qualitative identification using library search in GCMS. And it has also got very good quantification capability. You can do absolute quantification also using quadruple systems and easy to use. So these are some of the important features of a quadruple system. Now, when you actually analyze the sample by GCMS, there are two different modes of analysis. One is called a scan mode of analysis. Second one is called a SIM mode of analysis. Scan mode is normally used for qualitative analysis, not generally used for quantitation. It's only for qualitative analysis. So tomorrow, if you are going to have a GCMS in your lab, and if you have got a sample to be analyzed, what is the first thing you have to do? You have to decide what is the mass range between the sample is to be scanned, lower mass range to upper mass range. Suppose, for example, I am going to scan my sample between 40 AMU up to say 400 AMU or 500 AMU. That means lower side, it is 40 AMU I am fixing, and upper side I'm fixing 400 AMU or 500 AMU. So my sample fragments which are formed between 40 AMU and 500 AMU all will be seen by the detector. So this is called the scan range. Similarly, the case of when suppose tomorrow if you are going to record the spectrum of a compound in FTIR, IR spectrum of FTIR, then also you have to keep a scan range. Normally we keep 4000 inverse centimeter to 400 inverse centimeter for scanning the compound for recording the spectrum in an FTIR. 4000 to 400. That's the normal scan range we use in FTIR. So similarly, in the case of GCMS also, you have to have a scan range. Normally we use 40 on the lower side, 400 or 500 on the upper side. And this we can change also. I am just giving a normal list. And whatever fragments are produced from the sample molecule between this 40 and 400 will be seen by the detector. And then accordingly, it can give you, it can go for a library search, it can give you a qualitative identification. So scan mode is normally used only for qualitative analysis. But if you want to do a quantitative analysis, you have to use a different mode, which is known as SIM mode, selected ion monitoring mode. Used only for quantitative analysis, never ever do a qualitative analysis by SIM mode. You will get a totally wrong result. SIM mode is to be used only for quantitative estimation. That's all. Selected ion monitoring, you have to select the ions. As a user, suppose my sample undergoes ionization and it is going to give me, say, 20 fragments, 20 ions or 25 ions. I am not interested in all the 25 ions. I am going to do a quantitative estimation of the compound. I am not going to identify the compound. So out of these 20 ions or 20 fragments or 25 fragments, I will select maybe some 3 or 4 very, very prominent fragments. That is all. I want only 3 or 4 or 5 very prominent fragments. Rest of the fragments, I am not interested. So I am selecting, say, 1, 2, 3, 4. I am selecting the ions. And that is why it is known as selected ions. So you have already selected these ions. And then in the software, you have to feed these are the ions to be monitored by the detector. Okay, so when you actually analyze the sample, the detector will look only at those ions which you have selected. Other ions will not be seen by the detector. They will be totally blank. But what is the advantage? Much more sensitive than scan mode for quantitation. You get a very sensitive quantitative analysis using a SIM mode of operation. I'll just show you an example like here. We have analyzed a compound which has given more than 15, 20 ions. And we have selected 3 prominent ions, only 3. 54 mass number, 72 mass number, 152 mass number. That's all. And when I'm giving these 3 fragments in the software will make 3 different compartments because I have selected 3 different ions. First compartment, it will keep 54, second compartment 72, and third one 150. And then what the software will do, it will assign a DC to RF ratio which can only see 54, and that ratio will be fixed in compartment number 1. In second compartment, it will fix a different DC to RF ratio which can see only 72. And the third one, it can only see, that ratio can only see 152. So we have only 3 different DC to RF ratios, one for 54, one for 72, one for 152. When any other comes to detector, the detector will not be able to see because we have not fixed any ratio for them. So only these 3 fragments will be seen. You get a much better sensitivity for quantitation. But this can be used only for quantitative analysis. Now, what is the importance of vacuum? I told you vacuum is also a very, very important factor. A vacuum has to be a good one and vacuum has to be a clean one. Vacuum is supplied. See, when any vacuum system, when you break the vacuum, outside air will go inside. And all of us know that. Outside air means it contains nitrogen, it contains water vapor, it contains oxygen, it contains carbon dioxide. All those residual gases are there in outside air. So similarly, when you break the vacuum in a GCMS equipment, air goes inside, your ion source will contain air molecules. And you imagine you are not applying vacuum. You are directly starting the analysis. Just a hypothetical this thing. You are starting the analysis. You are not applying any vacuum. What will happen when your sample undergoes fragmentation and there are a lot of nitrogen molecules, there are a lot of water molecules, a lot of oxygen molecules because of the air inside. Your sample fragments will collide with all these gas molecules, like it will collide with nitrogen, it will collide with water vapor, it will collide with oxygen. There will be tremendous formation of background noise. And the background noise is going to be so much, your sensitivity is going to reduce drastically. That means you are going to lose your sensitivity and you are going to get a very noisy baseline. Sensitivity is practically gone. So to avoid this, what is to be done is all these residual gases should be pumped out as much as possible. It should be taken out. That is the reason why we are connecting this to a mass spectrometer to a vacuum pump. By starting the vacuum, we are trying to pull out as much as possible all these water vapor, nitrogen, and oxygen from the system, so that these type of collisions will not take place, background noise will be minimized, sensitivity will be increased. And that is what is the importance of a vacuum. So we have two different types of vacuum pumps in a GCMS. One is called a rotary pump, which is kept outside the system, just below your table where the mass spectrometer GCMS is kept. And that is designed to give a certain initial vacuum, 10 to the power of -3 torr. And then the final vacuum will be created by a pump is called TMP, turbomolecular pump, which is inside the system that you cannot see. It is inside the mass spectrometer. The TMP will take the final vacuum to the tune of 10 to the power of -6 torr. And initially you have to create a pre-vacuum. If pre-vacuum is not created, what will happen? There will be air molecules inside, and when the TMP is starting, and TMP has got very, very fine blades, and you can imagine what will be the rotation per minute, RPM of a TMP. It is approximately 90,000 per minute, 90,000 rotations per minute. That is the speed with which a TMP is rotating. So if there are a lot of air molecules inside, when the TMP blades are rotating at such a fast speed, because of the air friction, the blades will be spoiled. TMP will have to be replaced. Going to be a costly affair. So to avoid this, we are always creating a pre-vacuum with the help of a rotary pump. That is why we create a certain amount of vacuum, 10 to the power of -3. That means a huge portion of the air is already taken out. Then we start the TMP and it will take the final vacuum to the tune of 10 to the power of -6. Good vacuum is always, it will always reduce the noise level and improve the sensitivity of analysis. Okay. And this is, of course, this is how a GCMS looks like. You have got a GC on the right hand side, you can see, and the MS on the left hand side. There is an injection port where you are going to introduce the sample. There's a column inside. You can see a capillary column inside, and the column is entering the mass spectrometer through a interface. Interface is nothing but the bridge between the connecting bridge between the GC and MS, and that's also heated because when the sample is passing through that, if the interface is not heated, there is a possibility that sample vapor may condense. So to avoid that, we are normally heating. So heated interface, and the sample will enter the ion source. I've already marked it, ion source, where the sample will undergo ionization, and then it will be separated by the mass analyzer. You can see that. And at the end of the backside of the mass spectrometer, the mass analyzer, I have marked it as detector. That's your EMT tube. Okay. And below the ion source, you can see a TMP, turbomolecular pump. That's a pump inside the mass spectrometer. And there is a rotary pump which is outside the equipment. That is below your table. Okay. So these are basically main components of GCMS. Okay. Now, variable ionization voltage is normally a feature of the software. Normally, when you are having a ionization technique by 70 electron volt in electron impact, 70 electron volt is the default is the ionization voltage. Okay. But there is a provision in the software. If you want, you can reduce it. If you want, you can reduce ionization voltage, And what is the advantage of reducing the ionization voltage? Suppose if you are reducing the ionization voltage in electron impact ionization mode, there is a possibility that you may be able to see a prominent molecular ion. Thereby, you will get some information about the molecular weight of the compound. Okay, I'll just show an example here. You can see at the bottom. So there are three different ionization voltages. By default, 70 electron volt. The sample has undergone very severe fragmentation, and there is a very small ion I have shown as the M plus, the molecular ion. But I'm not very sure whether it is a molecular ion, whether it's a noise peak. I do not know. So what I did, from 70 electron volt, we reduced it to 40 electron volt. When you reduce it to 40 electron volt, what is your observation? The intensity of the last ion, M plus, it is increasing. And further, we came to 20 electron volt. You can see that M plus peak has got enhanced. The intensity has got enhanced. That means that is actually the molecular ion peak. That means I am getting an information about the molecular weight. This is a feature given in the software that's called variable ionization voltage facility and given by most of the manufacturers. Okay. Now, fast mode of analysis, I told you how we can reduce the analysis time and increase the output. This is the requirement in the corporate world. Okay, now to do this fast mode of analysis, there are certain hardware requirements. And all these hardware requirements are by default in our system. Our single quadrupole, latest single quadrupole system is called QP2020NX. And in this, all these hardware requirements are coming by default. Very high oven heating rate, very high column head pressure, high split ratio, high MS scan rate. All these are by default you are getting. Okay. So what is the utility of this fast mode of analysis? I have shown two examples. It's a perfumery sample. You can look at the two mass spec. One is the normal GCMS analysis of a perfumery compound. The same compound is analyzed under fast GCMS mode. At the top, it is normal one. At the bottom, it is fast mode. See, if you look at the normal GCMS analysis, you understand that it has taken approximately 50 minutes to complete the run. Almost 1 hour. 50 minutes, 55 minutes, almost 1 hour. The same sample, when I am analyzing by a fast mode, you can see how much time it has taken. It has taken approximately 7 to 8 minutes time, less than 10 minutes time. With a run which was getting completed in 1 hour in a normal mode, we are able to complete in less than 10 minutes time. But then when we speak to the people, they will have a concern. What will happen to the resolution? Something which was getting completed in 60 minutes, you are trying to complete in 10 minutes. What will happen to the resolution? This is the answer to that. Normal GCMS analysis and fast GCMS analysis, we are not compromising on the resolution at all. Resolution is exactly same. Only we are reducing the analysis time. How do we do that? We change the column. In normal GCMS, we normally use a 0.32 mm column, maybe a 50 meter long column, 0.5 micrometer film thickness column. That is the normal column which we use in normal GCMS for such a complex sample. Now, for fast mode, we are going to use a microbore column, 0.1 mm ID. Instead of 0.32 mm ID, we are going to use a 0.1 mm internal diameter column. Instead of 50 meter length, we are going to use 10 meter length. Instead of 0.5 micron film thickness, we are going to use only 0.1 micron film thickness. Ultimately, the column type is different. Okay, the efficiency of the column is exactly equal. And we are able to get the same type of resolution, even though we are trying to reduce the time. So we have succeeded in reducing the time from 50 minutes to 10 minutes, but we are not compromising on the resolution. So this is called a fast mode of analysis, which we can do in our system. Now, this is a DI probe. When I showed you the flow chart of a GCMS, instead of injecting the sample into GC, I have also shown an arrow direct inlet. whereby you can introduce the sample directly into a mass spectrometer. This is an optional accessory for the GCMS, but this is a very prominent accessory that is used in pharmaceutical industry. We are promoting this only in pharmaceutical industry because only pharmaceutical people will require this. I cannot promote this in the food industry because it is of no use. Because here the concept is your sample has to be a single compound. It has to be a pure compound. So if I have got a multi-component sample like a perfumery sample or a food sample, which may contain maybe 50 or 60 or 70 or 100 compounds in the sample, I cannot use a DA probe there. But I can use a DA probe in pharmaceutical industry. Pharmaceutical samples are many times you are working single drug, pure drug. And then instead of injecting into GC and waiting for the compound to come out of the column, you can directly put the sample into the mass spectrometer without affecting the vacuum. So there's a vacuum lock system. You can put the sample into mass spectrometer and you can complete the analysis in hardly about 5 to 6 minutes time. So what you see on the left-hand side is the probe. It's not a very big probe. This probe I can put in my pocket also. It's a very small one. And there is a very small quartz cup where you have to put a small grain of the sample. If it's a solid sample, just a few grain of the sample is required. If it's a liquid sample, you require hardly 1 microliter of the sample. This sample you have to put in the quartz cell, and this quartz cup will remain at the head of the probe, DA probe, direct inlet probe. And then this probe can be pushed into the mass spectrometer and you can get the complete information in a very small period of time. And this also has got other things like it can go to 500 degrees centigrade. We have got 5 different ramping heating rate, 5 degrees, 10 degrees, 20 degrees, 40 degrees, and 80 degrees centigrade per minute heating rates also. So even if the sample is a non-volatile sample, because of the temperature, because of the vacuum, you can analyze the sample without any problem. Okay. This is a drug analysis reserpine, and we have used a DAMS analysis for that. It's not a GCMS analysis, it's a DAMS analysis. And there are different accessories that are available for GCMS. You can connect an auto sampler, you can connect a headspace sampler, you can connect a purge and trap system. For environmental applications, we can connect a thermal desorption system. For polymeric characterization, we can connect a pyrolyzer system. So there are different types of accessories that are possible. They all can be connected to a GCMS. And coming to the last part of what are the major applications of GCMS? It has got fantastic applications in many different sectors. Pharmaceuticals, number 1, pesticides, perfumery analysis, food chemistry, petroleum, polymers, environmental applications, biomedical applications, forensic applications, spices and essential oils, textile applications, ROS applications, biofuels, biotechnology. There's a long list of segments where you can have many meaningful applications for GCMS. In GCMS in pharmaceuticals, number very prominent application is residual solvents. You are all pharmaceutical people, you know. If you residual solvent analysis is the requirement. USP method 467. If you look at USP method 467, it describes the estimation of residual solvents in API. Once upon a time, it was known as OVA, organic volatile impurity, but now it is renamed as residual solvents. The method is 467, and USP recommends 3 different procedures. Procedure A, B, and C. A is for identification, B is for confirmation, and C is for quantification. Columns are also different. Capillary columns are also different. So it's a purely USP method, and for which you require a GC along with a headspace sample. You cannot do it only with a GC or GCMS. You have to connect a headspace sampler attachment to the GC or GCMS. Then only you can do this. Okay. And I'll show what is a headspace attachment. Then identification of intermediates in API manufacturing, impurity profiling of finished API, analysis of raw materials, molecular weight of pure drugs, analysis of packaging materials in pharmaceutical industry, leachables in the extractables. There are so many different applications available for GCMS in pharmaceutical sector. Now, this is what is my headspace analysis. You all must be knowing what is a headspace analysis. It is nothing but an injection system. Headspace is nothing but the analysis of a volatile compound in a non-volatile sample. Analysis of a volatile compound in a non-volatile sample. That is all what is known as headspace analysis. Your sample is non-volatile. You cannot directly inject into GC column. You will spoil the column. At the same time, there is a compound which is volatile, which is present in the sample. I want to identify that. I can give a very simple example for you to understand. It's a forensic application. Alcohol in blood. People consume alcohol, and once you consume alcohol, after some time, it will come in the bloodstream. If you take out a small quantity of blood, like 1 ml of blood, and blood is a biological liquid, you cannot directly, it is totally non-volatile sample, serum, plasma, all those. If I directly inject into my column will be spoiled. My injection port will be highly contaminated. So a lot of process, I cannot do that. At the same time, I am interested in finding what is the alcohol content in blood. Alcohol is highly volatile. Blood is non-volatile. So we cannot directly inject. So we go by headspace analysis. So for example, here, there's a 22 ml vial. That's a standard universal vial for headspace analysis. We take about 1 ml of sample, say for example, 1 ml of blood. And 22 ml is the capacity of the vial. Then close it with a silicone septum, rubber septum. And over that, we are going to keep an aluminum cap and we are going to crimp it. Crimping means sealing. Once you crimp it, it becomes totally sealed. Nothing can go inside, nothing can come outside. And then this bottle will be put inside. The headspace sampler has got a small oven inside. All these will be done automatically. These are all automatic operations. The vial will go inside the oven and you have to heat it. And you have to optimize what is the temperature required. That's called an equilibration temperature. And how much time you have to maintain that temperature. That's called the equilibration time. The equilibration temperature and the equilibration time both have to be optimized by the user. Now here, I am taking a small blood sample. I am heating the sample. When I am heating, nothing will happen to blood. It's a totally non-volatile, but alcohol will vaporize because it is highly volatile. But these vapors cannot escape because the bottle is sealed. So in the bottle, alcohol vapor will accumulate. And after a certain period of time, a certain quantity of the vapor can be automatically transferred into the GC column by two different ways. One is called a syringe mechanism. That is what you see here. A syringe will come automatically. It will pierce the septum, take out a certain quantity of vapor, and then it will go and inject into the GC. So that means only the vapor has gone inside. Your liquid sample, your blood sample has not gone inside. You get a very sensitive analysis. Column contamination will not come. Injector contamination will not come. And analysis can be completed very fast. This is called a syringe mechanism. But nowadays, as per the regulations or USP regulations, we cannot promote a syringe mechanism in pharmaceutical industry. We require a transfer line mechanism. Instead of using a syringe, a certain quantity of the vapor can be automatically transferred to the GC column with the help of a transfer line, Q-silica transfer line, and that is called a transfer line mechanism. So there are two mechanisms. One is a heated syringe mechanism, and one is a transfer line. So now the transfer line mechanism is what is used in pharmaceutical industry. A certain quantity of vapor can be automatically transferred to the column. Okay, so now this is the equipment which we are providing. This uses a transfer line mechanism. And this is what we are promoting in pharmaceutical industry now, which is called HS20, one of the most powerful headspace analyzer in the market today. This is originally designed and manufactured in Japan, Shimatsu, Japan. And it uses a transfer line. You will not be able to see the transfer line because the transfer line goes from inside. It's only 30 centimeters long, internally going inside. And the vapor will automatically go to the GC column. So this is called a transfer line mechanism. This is an example of API, class 1 solvent analysis. And the USPS classified the residual solvents into 3 different classes. Class 1, most carcinogenic. Class 2 is less toxic. And class 3, by and large, non-toxic. Class 1 and class 2 solvents are to be done by gas chromatography and headspace. And class 3 solvents can be done by loss on dry, LOD. Okay. So this is an example of class 1 solvents, most dangerous solvents, 1,1-dichloroethene, 1,1,1-trichloroethane, carbon tetrachloride, benzene, and 1,2-dichloroethane. They're all well separated on the baseline. We have used a 624 RXI 624 SIL-MS column, 0.32 mm ID, 30 meter long, and 1.8 micron film thickness, high resolution capillary column we have used. And we could separate all these on the baseline and perfectly quantify them after creating a calibration. And this is a CA spectrum of a pharmaceutical drug analyzed under positive chemical ionization mode. And looking at the spectrum, you can immediately understand what is the molecular weight of the drug, because you are getting M+1 at 208. So the molecular weight of the compound is 207. This is DI analysis, direct inlet. For example, we have analyzed the steroid, prednisolone. Steroids cannot be directly injected into GC because they are non-volatile compounds. We can analyze steroids also by column, but before injecting into column, we have to do a derivation. We have to convert it to TMS derivative. All steroids should be converted to TMS derivative, trimethyl-silyl ether derivative. So there is a derivation procedure involved. TMS derivation reagents are costly, and there is a time factor. All those are there. But if I have got a DI probe, instead of doing all those, I can directly put the sample into MS. So this is called a DI-MS analysis. On the left-hand side, you can see prednisolone. On the right-hand side, you can see reserpine. And most importantly, we are completing this analysis in hardly about 5 to 6 minutes. And these are herbal drugs. Herbal drugs are highly polar materials. They will require very complex derivatization if you want to inject into the column. But if you have got a DI probe, you can directly push into the mass spectrometer and you can complete the analysis. Genotoxic impurities in API manufacturing. And you all know, because I don't have to tell you what genotoxic impurities, that possibly they're all forming as a part of the manufacturing process. There are different types of genotoxic impurities. And if they are identified and they are then possibly you'll have to make a lot of changes in the modifications in the process. I mean, thereby minimizing the production of genotoxic impurities. One of the prominent groups are sulfonic acid esters. For example, methane sulfonic acid ester, benzene sulfonic acid ester, paratoluene sulfonic acid ester. These are all genotoxic impurities. So we have separated and quantified for about 12 genotoxic impurities in this mixture by GCMS. Of course, you require standards if you want to do quantification. So that is absolutely essential. Another class of genotoxic impurities is alkyl halides. So here also we have quantified around 19 different alkyl halides, which are possible genotoxic impurities in API manufacturing in pharmaceutical industry. Another latest requirement all of you must be knowing is nitrosamines, presence of nitrosamines in drugs. Nitrosamines are extremely carcinogenic compounds. There are about 6 or 7 different nitrosamines which are identified, and they can be quantified by GCMS, MS, or even LCMS, MS. Okay. So I'm just showing 2 examples, NDMA and NDEA. N-nitroso dimethyl amine and N-nitroso diethylamine. And we have also optimized a method for the separation of all the 6 different nitrosamines by GCMS. So that also method is available with us. So here we have gone even quantification, absolute quantification we did. Okay, so this is, we prepared a calibration curve from 2.5 ppb to 10 ppb, and we did an absolute quantification. And for different companies, we have done this. Different pharmaceutical companies we have done. I mean, nitrosamines in metformin and many different analysis we have carried out in the Shimadzu lab in Mumbai. These are all data produced in Shimadzu lab in Mumbai. Then extractables from a pharmaceutical packaging, you all must be knowing leachables and extractables. That is another requirement as per USP in pharmaceutical packaging material. And there are different methods of doing that. I mean, you can go for a liquid extraction and then directly injecting into GCMS. You can go for a thermal desorption connected to GCMS, or you can go for a dynamic headspace and attachment along with a GCMS. That also can be done. So these are all different solvents, which are extracted from a pharmaceutical packaging material. Hexane, dichloromethane, ethanol. These are three solvents we have identified by a very, very simple technique. Coming to GCMS and biomedicals, that's a very upcoming area, basically for neonatal screening, NBS, newborn screening. When a child is born, we can actually take a urine sample at a very, very early stage and find out whether the child is having any major genetic or metabolic disorder. In that case, the physician can decide what is the treatment to be started. So the child grows up, it will have no major complications in future. So what is the starting material? Urine is the starting. You see, any healthy human being, because of the metabolism, human metabolism, lot of carboxylic acids are getting generated inside our body. And all these carboxylic acids are getting excreted through the urine. And if you take the urine sample and if we extract the carboxylic acids, we clean up and purify, and then we derivatize it, and we inject the GCMS, we will get a carboxylic acid profile. A healthy human being has got a certain carboxylic acid profile. But if the person has got some defect, the carboxylic acid profile will change. And then we have got a separate software for that. IEM software, inbound errors of metabolism software. So that software we supply along with our GCMS, and then using that software, the disorder the child is having can be identified. We are given almost about 8 to 10 systems across India, different hospitals and different testing centers. And this is a urine sample. This data was generated in Shimadzu, Japan. The urine sample is taken from a child after 3 days of birth. And then it contains a lot of extraction is required, cleanup is required, because urine is a biological sample, a lot of matrices could be present. So a lot of extraction, cleanup, purification, and then derivatization, all these required, and then you can inject into GCMS and you can apply the software also. GCMS in food analysis, flavoring compounds, there are so many different flavored foods are available in the market. They are not natural flavors, they are all synthetic flavors. Synthetic chemicals they are adding. For example, pineapple flavor, they are adding certain chemicals which will give a pineapple flavor. So we can identify all those, what are the chemicals the manufacturer is adding, which gives a certain flavor. We can use a GCMS along with a headspace sampler. Identification and estimation of residual pesticides in food, which is a global problem today. Whatever we are eating, whatever we are drinking, they all contain pesticide residues. It's a global problem. There are a lot of regulations, European Union regulation, a lot of regulations are FSSAI is there. There are a lot of regulations regarding the food quality. And this is normally nowadays we are doing it by GCMS-MS or LC-MS-MS. Similarly, determination of residual solvents in packaging material. That's also very, very important application food industry, which we can do by GCMS in combination with a headspace sample. This is coffee aroma, because coffee aroma, when everyone likes a hot cup of coffee, but that aroma is a very, very complex sample. It contains so many different compounds in the coffee aroma, which gives that flavor for the coffee. We have used a SPME method. SPME stands for solid phase micro extraction. It's also an extraction technique. SPME along with the GCMS, and we have identified all the compounds in the coffee aroma. So many compounds are, so many chemicals are there in coffee, and that is what is giving the flavor for the coffee. And this is analysis of pesticides in food products by GCMS. Today is a very burning topic. It's a global problem. And we are normally using a GCMS-MS or a LC-MS-MS for this. And In our Shimadzu lab, we have optimized a method on GC-MS-MS where in a single injection, we can separate and identify and quantify 450 pesticides in a food sample. Also, that data is also available with us. And this is the last slide. I mean, this is a typically forensic application, alcohol in blood, using a GC, MS, and FID with a headspace. Along with your GC-MS, you can add other detectors also. On a GC-MS, you can attach an FID. So when the compound is coming from the column, there is a provision. You can split this compound into two parts. And that is what is known as column splitting. And when the compound comes out of the column, it will be split into two parts. One part will go to MS, one part will go to FID. So in a single injection, you can get an FID response. You can also get a MS response. This is called column splitting we can do. Okay. So, so this is a GC-MS FID along with headspace sampler, alcohol, blood alcohol. And this is a typical forensic science application. So if you look at this, it's a very major area. There are so many applications. I've only taken out few applications for your information. And Shimadzu has got now the current, we have got 3 different models of GC. Nexus GC2030 is the top of the line model, the latest model, which having very, very advanced model, having lot many features. That's the model, Nexus GC2030. Then below that, we have got another model, GC2010 Pro. And then most economical model, GC2014. Means that's 3 different models we are having. And in headspace samplers, we are having 2 models. HS20, as I told you, is one of the most sensitive headspace sampler available in the market today, HS20. And 90 samples we can analyze at a time. And then we have got one more model called HS10, where we can analyze 20 samples at a time. Both are using transfer line mechanism. And then we also have got GC-MS, single quadrupole as well as triple quadrupole. In single quadrupole, we have got 2 models. GC-MS 2020 QP2020NX is the very powerful single quadrupole GC-MS. And then we have got a low-cost MS also, which is called GC-MS QP2010SC. I mean, this doesn't have that many features like 2020. It's basically meant for routine applications. And then we have got 2 models of triple quadrupole MS-MS, GC-MS TQ8040NX and GC-MS TQ8050NX. 8050 is the latest model, very powerful system, advanced model. That's the top of the line TQ model. So we have got 2 TQ models, 2 triple quadrupole MS, 2 single quadrupole MS, and then 3 different models of GC and 2 different models of headspace. Then we have got all other accessories like auto samplers and headspace sampler. Other than this, we have got syringe-based auto samplers, headspace samplers also, like AOC 6000 that is working on syringe mechanism. That is why I have not shown here, because normally in pharmaceutical industry, we are promoting a transfer line mechanism. Then we have got pyrolyzer, but that is not relevant for you. Pyrolyzer is basically in polymer industry. And then thermal desorption system for environmental analysis, and the purge and trap system for water analysis. So all those other accessories are also available. So we have got different accessories to meet the requirements of different segments of our customers for various applications. And we have got a customer support center in Mumbai, where we can show the demonstration, we can show the capability, we can analyze samples for you if you want. All those. So we have got a fantastic, well-equipped customer support center in Mumbai, Andheri. And anytime any of you want to visit our center, you're all most welcome. You can contact our Pune office. I think Vishal is there, from my colleague. Vishal is there in this group, I think. So you can always contact Vishal, the Pune office. And then we are most welcome to visit our lab. And with this, I finish my small discussion on a single quadrupole system. And I am well within the time. It's only 4:20. My time is up to 4:30. We have got another 5 minutes. If at all any participant wants to raise any question. Over to you, sir.
Yeah, Umbarkar sir, please.
Yes, sir. Any questions on the topic, sir, discuss with us? Participants, any questions?
Yes, participants, if you have any question, you can ask directly by unmuting your mic.
If any other participant in the future want to contact me, you can also do that. You are most welcome, available for any of you. And Manoj sir is having my contact details, my mobile number and email ID sir is having. So you can contact Manoj sir, you can get the information, you can always contact me for any sort of clarification, for any sort of help, whatever is possible from my side.
Hello. Yeah.
Yes, Satyanarayan sir. Yes.
Hello. Am I audible?
Yes, yes, you are audible, sir.
Yeah. Thank you. Thank you for the wonderful lecture regarding GCMS. I just want a clarification. The thing is, with Simartsi system, the GCMS libraries are available for the standards?
Yes, sir. Libraries are available. We have got both the libraries, standard libraries like NIST libraries available, Wiley libraries available. And then we have got additional libraries like drugs library, pesticide library, polymer library, toxicology library, different libraries are available. But when you buy a GCMS system, by default, you will get a NIST library latest version, which contains more than 3.5 lakh mass spectra.
Okay, because actually presently we have Agilent system, which we don't have. This because it's a little bit older version. Okay.
Now, sir, when you buy, you will get a library automatically. Mostly, it will come with an NIST library.
And if you suggest me, if at all, if we want to go for a new system, what could be the version, the latest version for this?
If you are considering a single quadrupole system, the latest version from our side is QP2020NX.
For 1 minute, which one?
Yeah, you can see my slide now. GCMS QP2020NX.
Acha, QP2020NX.
That's a single quadrupole system. Very, very powerful system, sir.
Okay.
Sir, can I get your more information, sir? I mean, you are from which college?
I am from Pune College of Pharmacy, Bharati Vidyapit, Pune.
Acha, Bharati Vidyapit, Pune College of Pharmacy. Your name, sir?
Satyanarayan.
Acha, Dr. Satyanarayan. Okay. Bharati Vidyapit, Pune College of Pharmacy. Okay.
Yes.
Okay, my colleague, I think Vishal, my colleague from Pune office is, I think he is also there in the group. Vishal, are you there?
Yes, sir. Good afternoon, sir.
Acha, Vishal, you can contact sir.
Yeah. Actually, I am in discussion for the UV with the Satya sir teams also. Dr. Amarjit and Dr. Hemant Jain, right, sir?
Yeah. He told me. He has given me your quote and all. Yes.
I will meet you, sir. No problem. I will come and meet you.
Okay. There was some discussion regarding upgradation of our food testing laboratory, where important thing is GCMS and LCMS-MS. So that's what I thought.
Okay, sir.
Okay. Anyhow, we'll talk to Vishal once he come here. I can talk to Mr. Vishal.
Right, sir.
Thank you. It was a good session. Thank you.
And thank you, sir. Thank you.
Yes, Umbarkar, sir.
Yeah. So, sir has delivered a very nice session. Has given a thorough knowledge of instrumentation of GCMS with its practical applications. Sir has discussed the problems that may arise while using mass spectroscopy and also told the solutions for them by giving several examples. So, sir has also discussed the accessories that can be used with the mass spectroscopy and various biological applications of GCMS in a very simple language. And sir, really, it was a nice experience and was easy to understand. And it can be reflected in the comments shared by the participants in the chat box. Sir. So now it's a time to propose a vote of thanks. Sir, I want to share my slide. Okay, so your slides will not be visible then.
Yeah.
Yes.
So sir, I want to thank all the participants for giving me a very, very patient hearing for almost 2 hours. I know it's very difficult for us, all of us, to listen to a talk, especially after lunch. But all of you had given me a very patient hearing. I thank you so much. And I'll be meeting you once again on 3rd of March for another session on UV spectroscopy. Okay, so that will be in the pre-lunch session, and that also I hope to make it a very, very interesting discussion.
Yes, sir. Yes, definitely, sir.
Thank you, sir. Thank you once again.
Yes. Can you
So,
present
sir,
the certificate, please?
Yes. My slide is
Yes, visible.
Yeah, sir. So for this nice session, on behalf of entire fraternity of the Government College of Pharmacy, Karad, I extend a really hearty vote of thanks to Mr. Giriraj, who spared time from his busiest schedule to enlighten our participants on the GCMS and its core concepts in a very easy manner. Thank you very much, sir, for such a nice and informative session. And I'm sure all the participants are benefited with the concepts you shared with them. Now it's time for the appreciation of our guest speaker. For this, I request Dr. Manoj Charde, sir, to offer a certificate of appreciation. Please, sir.
Girijan, sir, please accept this certificate,
Thank you,
virtual
sir.
certificate from
Thank
our
you.
side.
Thank you, sir. I'm accepting it with all gracefully. I'm accepting it, sir.
And I'm very much thankful to you. Continuous for 2 hours, you have delivered a very nice session, and it was a very informative also. So that's why everyone hear you.
Thank you, sir. Thank you.
And thank you, Vishal, sir, also. Can you present the certificate, Rahul, sir?
Yes. Sorry, it is visible?
No,
sir.
only
No.
thank you slide is visible.
Okay.
Go to the next slide. Yes.
Yes.
Yes, sir. This is
Okay.
certificate for you, sir.
Okay, sir. Will you be able to mail it to me, sir?
Yeah. Definitely will mail
Okay.
you, sir. No problem.
Thank you, sir. Thank you so much. I enjoyed the session.
See you on 3rd.
Okay, sir. Thank you very much.
Thank you.
And all the participants, thank you very much. And have a wonderful evening.
Thank you, Vishal, sir. Thank you very much.
Okay, sir. I will log out now.
Yeah. Okay.
Thank you, Dr. Manoj Charde, sir.
Yeah, thank you. Bye, sir.
Thanks.
Bye, sir.
Bye, sir.
Pandey, sir. Next speaker has joined.
Yeah, sir. I am here.
Yeah, good. Venkatesh, sir. Are you there?
Good evening, sir. Yes, I am here.
Yes. Okay. Pandey, sir, you can proceed.
Yeah, please make me co-host.
I have already made you co-host.
Yeah, sure. Thank you. Okay, is my screen visible?
Yes, sir.
Okay, so let us start today. Good afternoon, everyone. Today we have a very eminent speaker with us, Mr. Venkatesh. So before starting the session, let me introduce our speaker, Mr. Venkatesh. Currently, he is working with Bruker Deltonics as an application specialist since 2014. He was mass spectrometry facility in charge in Indian Institute of Sciences, Bangalore. He was MS product specialist in Hyderabad, and he was associate scientist in Syngene International Limited Biocon Park, Bangalore. He has completed his education in biotech, postgraduate in biotechnology, Bangalore University, India, and he has worked as project assistant and research associate in clinical molecular biology division, Bangalore. I request Principal KB Burade sir to please welcome with a bouquet.
Thank you, sir.
Thank you, sir. So I think we will start our session. I request Venkatesh sir to please start with the session.
Venkatesh, sir.
Yes, sir.
Before this, we have GCMS, right?
Yeah.
So he have taken exhaustive session. So you
Yeah.
can talk on the important things of that MS, so that we can wind up by 5:30.
I'm not going to take more than 40 minutes, sir.
Yeah, yeah. Okay. Thank you, sir. Thank you. Thank you.
My screen is visible for you people.
Yes, sir.
Or if you people want to take any 5 minutes break like that, please, you can.
No, you may continue, sir. No problem.
Yeah, fine. Thank you. So already from afternoon, you are having continuous sessions regarding HPLC, mass spec. First of all, thanks for inviting for this session, and thanks for your introduction, sir, Pramod sir. And in my session, we will discuss about mass spectrometry applications. This is completely dedicated for pharma, biopharma, and some different models of mass spec, and which mass spec is useful for which kind of requirement, which kind of application, we will discuss one by one. This is my agenda. Already you are discussing about mass spec continuously from morning. Just I will take a brief time for definition, history, types of manufacturing companies, different models, instrumentation part, what is the key points in mass spec. Then I will go to biopharma. What is the role of mass spec in biopharma? What is mass spectrometry? Mass spectrometry is a study of different molecule analysis by making them charge, by giving the charge for them. We are not going to measure directly any compound. We are activating the compound as a MYZ ratio, nothing but plus charge or minus charge. It's a negative mode or positive mode. You are going to give some charge for the particular compound. Then you will measure that particular compound by giving charge state. This is the history of mass spec. Previously, it started as a for lower molecules. Now we extended our mass spec till 700,000 Dalton. Sometimes it's reaching more than 1.8 million Dalton, 1.8 kilo Dalton and all. Previously, mass spec started as previous session. You would have already got the information. Previously, mass spec started as a GCMS, MS. Then, due to increase of our requirement, due to increase of our compound mass, from 1000 to 2000, 3000, 10,000. Now regularly we are analyzing 150,000, nothing but our maps, antibody. Like basing upon our requirement, automatically our improvement happen in mass spec. Day by day, different kind of technology introduced in mass spec, nothing like MALDI technology, TOF technology, Arbitrap technology, ion trap technology. Basing upon customer requirement, you can use different kind of models. For example, if you take here types of mass spec, we are having single quad. Already previous session, you could have understood what is single quad and all. Triple quad, ion trap technology, RB trap technology, Q-TOF technology, MALDI-TOF technology, FTMS. Like this one, you are having different kind of technologies in mass spec. And in another side, you can see what kind of companies you are having, different vendors from Brugers to Waters, Agilent, Cyax, Shimaju, Thermo, Geol, Edvion, different companies you are having. This is the outline of mass spec. In normal, any general mass spec technology, you will have initial inlet, starting position, ion source, analyzer, detector, data system. In inlet portion, you will have different options. You will have different options like GC, LC, CE, or otherwise you can directly inject your sample through inlet. So depends upon your requirement, you will have different inlets. Already you discussed about HPLC afternoon. HPLC you will have, UPLC you will have, GC you will have, capillary electrophoresis you will have. Otherwise, directly by using injection, you can load the sample. Next step is ion source. This is the part where your complete solvent, compound, whatever sample you are introducing to the mass spec, it will get evaporate. It will get ionized. It will get the charge. It will be APCI, ESI, laser power. By using laser, you can activate your compound. By using ESI, electro spray ionization, or you can use APCI, atmospheric pressure capillary ionization, EI directly, electron ionization. Like by using different ion sources, you will charge your molecules completely. You will evaporate other solvents, everything. Only your charged ions, your charged molecules will enter into analyzer. Ion source is the part where you will select different kind of ion sources, depends upon your kind of sample. Next, analyzer. Every sample not required HRMS, every sample is not required for MSMS fragmentation. Normally, when you are analyzing your molecule, as I mentioned in mass in previous slide, you will get the mass of that particular molecule sample. The units of Daltons. If it is 1000 Daltons, directly we will keep it as a shortcut kilodaltons, KDA. Okay. In this analyzer, you are having different kind of analyzers. As I mentioned in previous slide, ion trap technology, we are having TOF technology, time of flight. How much time it's taking your charged ion to reach the detector. That is called as TOF, time of flight. Okay, QTOF. You will have extra one more setup, quadrupole, TOF technology, triple quad. In single quad, as you observed in previous session, single quad, you will have only one quadrupole. In this triple quad, you will have 3 quadrupoles. Why we need 3 quadrupoles? Why we need QTOF instead of only TOF? We will discuss in next slides. And data system, whatever you are acquiring data, you will analyze the data. Here, most important, it's not only getting completely bunch of data, it's about how you are how you are doing the analysis of the particular raw data, how you are presenting the data, how you are concluding. Okay, these are the different models for as single quad, ion trap, triple quad, QTOF technology, multi-TOF technology, RB trap technology. Now we will see step by step instrumentation part. As I mentioned, oh, sorry, I'm not getting the pointer here. Just one sec. Yeah, see, as I mentioned as an outline of mass spec, here we will discuss about triple quad, ion trap. In triple quad, as I mentioned, you will have 3 quadrupoles. Quadrupole is the setup where you can use for 2 kinds. One, you can use it as a mass filter. Another one, you can use it as an analyzer. In this case, if you are having only single quad, means you are having only one quadrupole, it will work as an analyzer. When you are having a triple quadrupole, 3 quadrupoles, first quadrupole here, it will work it as a mass filter. Second quadrupole will work it as a collision cell. Third quadrupole will work as an analyzer. What it will do as a collision cell? Normally, when you are analyzing your molecules, if it is a single quadrupole, if you're not doing any MSMS, you will get it as an only mass, maybe 100 Dalton, 200 Dalton, or 300 Dalton. But how can you confirm exactly that is your molecule? Maybe same 100 Daltons, you may have sample X, at the same time sample Y molecular mass also same 100 Dalton. Then how can you confirm it's a sample X or sample Y? In that case, you have to break the molecule. For example, if you say 100 Dalton is your mass, when you are breaking your sample X, it may give it as a 50-50. When you break sample Y molecule, even though it's a 100 Dalton, when you break it into fragmentation part, it may result as a 75 Dalton and 25 Dalton. To confirm fragmentation level, here we will do MSMS fragmentation. Okay, for this MSMS fragmentation, we need collision cell. Here, for example, if you take, as I mentioned, inlet, here your inlet is there. Maybe it's a LC or GC. From here, your ion source is ESI. You can see here, through ion source, it's completely spraying your sample. Only charged ions are entering inside funnels. From there, ion bridge, where it will avoid complete other uncharged molecules, everything. First quadrupole will work as a mass filter. What is mass filter? When you are more concerned about only your molecule, when you are injecting any of your sample, it may contain even 20 Dalton, it may contain even 2000 Dalton also. But you want to concentrate, you want to check only your sample mass where it is 1500 Dalton. In that case, you will give your mass range, scan range only from 1000 to 2000. Automatically below 1000, above 2000, all molecules will be screened, filtered. This Q1 position, this quadrupole will work as a filter, mass filter. Only as per your instruction, as per your parameter, it will filter remaining all molecules, it will only allow whatever mass range you given. This is first quadrupole. In second quadrupole, as I mentioned, collision cell, here it will break the molecule. As I mentioned, if you want to check only MS, this collision cell will be in inactive mode. Directly your ions will pass through analyzer, you will get the MS mass. But you want to do fragmentation level, you want to do MS also. In that case, first you will get the filter in Q1, quadrupole 1. In second quadrupole, each molecule, each charged molecule will get into fragments. It will break into different fragments. Those fragments will enter into Q3, quadrupole 3, and you will get the masses. Here, you are confirming MS. At the same time, as a fragmentation level, you are confirming MS. Means your confidence level when you are saying as a only MS level, your compound mass, and MS level compound mass, it will be completely different. Same criteria when you come to ion trap. In ion trap, you don't have 3 compartments or 2 compartments. In ion trap, you will have only 3D mode, single compartment where MS both will happen. Okay, this ion trap will work by time base. Whatever we are discussing here, these all collision cell working, this filtration, scanning, everything will happen in nanosecond, not even in millisecond. In nanosecond, this and all will happen. This one will happen, this one will call it as a space fragmentation, this one will call it as a time fragmentation. What is the difference? In this space fragmentation, your filtration is happening in Q1, your fragmentation is happening in Q2, your analysis happening in Q3. Everywhere you are having step by step. Space, it's changing every time. As a compartment, it's changing every time. But in ion trap technology, everything, MS scanning, MS fragmentation, analyzing, everything will happen in same compartment as a 3D compartment. So you can observe here ion source, same as through LC, your sample is moving here. Charged ions are entered into glass capillary. From here, octopole, where it will filter and it will make it as an ion path only for charged ions. Through lenses, your charged ions will enter into ion trap compartment, where within nanoseconds, it will select the MS, whatever mass filter you given, it will select it and it will break it into MS fragments. And through detector, you will get the masses. Here, these all mass specs will work under vacuum with particular nitrogen gas, argon gas, depends upon your application. Your gases, what type of gases also will be changed. If you want to use it as a CID, you will use nitrogen gas or argon gas. If you want to do as a ETD, you will use methane gas. What is the difference between CID, ETD? We will discuss in next slides. Okay, by in the presence of nitrogen gas or argon gas, your molecule will break into fragments. Those fragments will enter into detector and you will get the peaks. Okay, these all whatever we are discussing here, these all are for MS scan, at the same time for MS scan. This is triple quad where you can observe clearly Q1, Q2, Q3, 3 quadrupoles are there. This one is ion trap technology where all this MS scanning, MS scanning, detection, everything will happen in same compartment. Now we will discuss other models. Q-TOF technology. What is the difference between Q-TOF and triple quad? Only the analyzer part will change. Instead of third quadrupole, here you will have TOF technology. Okay, same you can see here, spray chamber. Your sample is injected through spray chamber. Glass capillary is there where it will pass the charged ions. Funnel, through funnel it will go to hexapole where it will make it as an ion path. First quadrupole, as I mentioned in the previous slide, you can make it as a filter, mass filter. As per your mass range you given in parameters in your method, it will filter the molecule. Second quadrupole, nothing but collision cell, where it will break every molecule into fragments. Instead of in third quadrupole position, you are having TOF technology, where your ions will analyzed by TOF technology. TOF means time of flight. How much time your charged ions taken to hit the detector will be converted into MYZ. If it is a large molecules, it will take more time. As if you take heavy vehicles or normal bikes and all, bikes will move a little fast compared to larger heavy loads and all. Like this, if your molecule mass is more, automatically it will take more time to hit the detector. Normal small molecules and all, it will move very fast. Basing upon time of flight, how much time it's taken to hit the detector, it will converted into MYZ. Okay, this is Q-TOF. Actually, we have to call it as a Q-TOF technology. Why? Because 2 quadrupoles, 1 TOF technology. As a nomenclature, when you are explaining, you will say it as a Q-TOF technology. Another one is Arbitrap technology. As same, here also you will have 2 quadrupoles. First quadrupole for filter, second quadrupole for fragmentation. Instead of third quadrupole or TOF technology, you will have Arbitrap technology. In this mode, directly it will go through reflector and it will hit the detector. It's like a V shape, but here it's a orbital motion where your species separation will be more good. Okay, these all are called as HRMS, high resolution mass spec. When I am saying to separate two different species, if it is a 100 Dalton, 150 Dalton, I can separate it very easily. If it is a 100 Dalton, 110 Dalton, still I can separate very easily. If I say 99.89, if I say 100.89, the difference is only 1 Dalton. Like this, till 4 decimals, when you have to separate two closed species, you need very high resolution mass spec. In these cases only you need Q-TOF, Arbitrap, timsTOF technologies where they will separate very, very closed species. When I'm saying 100 Dalton, 200 Dalton, these are not going to be that much easy. Exactly, if I say that is like 100.0025, 100.0024, this much closed species also should get separate. In this case, we need Q-TOF technologies, Arbitrap technologies, timsTOF technologies to make separate. The third system is here, MALDI-TOF technology. What is the difference between Q-TOF and MALDI-TOF? The term itself, you can mention it as a MALDI-TOF. In Q-TOF, filtration, collision cell, TOF technology, you are having different compartments. And I am mentioning always in entrance in spray chamber, you can connect it LC, GC, CE, all other equipment. But in MALDI-TOF technology, MALDI, matrix assisted laser desorption ionization. Here it is ESI, electrospray ionization. Here it is laser desorption ionization. Here you are charging your ions by ESI, by applying temperature, pressure, and flow. Here you are applying charge for your molecules by applying laser. So your molecule will be mixed with some matrix as per your requirement. If it is a protein sample, synapic acid, if it is a peptide sample, CHCA matrix, like by different molecules, you can mix with the different matrices and you will keep the target plate into the instrument. Once you will apply the laser,